So, my name is Grazia Speranza. I'm from Italy, and I have the honor to serve as IFORS president since last year. I have the pleasure today to welcome you to the first IFORS global webinar dedicated to operations research in Latin America. Next slide, please. Yes, we are indeed getting through difficult times. Country after country, the COVID-19 has hit the entire globe. Wherever it is, wherever it hurts, the COVID-19 is hurting our community because we are everywhere. IFORS is close to the families and to the individuals who are suffering in these months. And I hope, that better times will come soon for all of us. Next slide, please. IFORS is the Federation of the Operational Research Societies, and it has at the moment 54 member societies organized in 4 regional groupings: NORA, ALIO, Euro, and IFORS. Next slide. And it has an administrative committee composed by the people you see on this slide. I would like to draw your attention now on the 4, click please, vice presidents representing the 4 regional groupings. Each of them has accepted to organize a global webinar, and I would like to express my gratitude to them for their effort. Next slide, please. The webinar that we will listen to today is the first of the IFORS global webinars IFORS has decided to organize, given that this year we will not have an opportunity to meet in person. And these webinars are for us an opportunity to get to know each other better. Next slide, please. As I said, the webinar of today is dedicated to ALIO, and the ALIO president, Guillermo Duran, will say a few words shortly. And Rosiane de Freitas will, after, introduce our speakers and chair the rest of the webinar. Willy, it's your turn.
Thanks a lot, Gracia. Thanks a lot, IFORS, for the organization of this webinar. I am Willy Duran. I'm the president of ALIO, and I am from Argentina. Please, next slide. Well, ALIO is the Latin Ibero-American Society of OR. It includes 11 societies of different countries: Argentina, Brazil, Chile, Colombia, Cuba, Ecuador, Spain, Mexico, Peru, Portugal, and Uruguay. Next slide, please. This society was created in Rio de Janeiro in 1992 in the occasion of the first CLIO, our conference. And since then, 19 CLIOs have been organized. Besides, the first Latin American Summer School of Operational Research took place in Chile in 1994, and since then, 23 editions of this school have been held. We also co-organized with Euro, the ALIO Euro International Conference on Applied Combinatorial Optimization. The first one took place also in Brazil in 1989. Next slide, please. Well, we have our conference, and next CLIO should be organized this year, but you know what did it happen in all the world, and now it was postponed to next year in the same week of the year, in the end of August, and we have 5 excellent plenary speakers. You can see in this slide the names of them. Next slide, please. We also have these forthcoming events, the IFORS International ALIO Socio Conference, which will be held in Colombia in next June, and the next ALIO Euro, International Conference on Applied Combinatorial Optimization in Viña del Mar in Chile in the end of 2021. This is our board. I am the president, and Antonio from Uruguay, Antonio from Spain, Rosian from Brazil, Jaime from Chile, and Juan Guillermo from Colombia are the other members of the board. Next slide. And this is our contact. We have I think, a very nice new web page you can visit. I think that there you have a good place to know what ALIO is organizing. Thanks a lot, and I think that Rosian is the following. Rosian?
You're on mute.
Yes.
Oh,
thanks,
great.
Rosian.
Okay. Thank you, Grazi and Willy Duran. I am Rosiane de Freitas, Vice President from IFORS, representing ALIO, and also in the ALIO committee. So it's with great pleasure that we begin the first webinar in the IFORS Global Webinar Series. In this first webinar, section ALIO, we discuss about operational research in Latin America, from theory to practice. We appreciate the presence of all of you. In this first webinar, we have 3 speakers from 3 different countries in Latin America. Marcia Fampa from Brazil, Andrés Medaglia from Colombia, and Roger Rios from Mexico. 3 great representatives in the Latin American and worldwide OR community. Thank you 3 for accepting our invitation. About the roles of this webinar, each panelist will have 20 minutes to give a lecture. Participants can send questions by chat at any time, but only the final, the panelists answers the questions. Okay? So let's start the first lecture that will give by Marcia Fampa from Brazil. Next slide, please. Okay. Marcia is a full professor at Federal University of Rio de Janeiro. She holds master and PhD degrees in system engineering and computer science at the same university in Rio de Janeiro, Brazil, and spent a year at the University of Iowa. And also after she was a visitor research at the same university. Her research interest is in optimization, particularly in mixed integer nonlinear programming and semi-definite programming. She has served as vice president of the Brazilian Operational Research Society, SOBRAPO, and she's the author of linear programming books. She has received awards throughout her career, has a strong presence in the international scientific community of mixed integer linear programming. So Marcia, thank you again. You can start your lecture. You have 20 minutes.
So I can share my screen now?
Yes.
Just a moment. So share. Can you see it?
Yes.
One moment, just for me to. Okay. Well, I'll start thanking Rosiane for the very nice presentation and also for the invitation. It's very nice to be here as a representative of the ALIO community on this first web seminar. And I'd like also to thank the organizers, Mary, Christy, and Grazia, for organizing this event. I think it's a very important thing for us to have our web seminars and our virtual conference during the pandemic to keep our interaction, right, on these difficult times. And I actually think that this is a nice outcome from the difficult times. I mean, I think the web seminars, especially the ones in conference, virtual conference, especially the ones that have no registration fee, this opened a lot the possibility for people all over the world to participate in our community, especially for new students, PhD students to present the work. So my suggestion is just we try to keep this alive even when the pandemic is over, to open the possibility for more people to interact and participate on our group. Okay, well, my talk will be about parametric relaxation for the quadratic knapsack problem. This is a joint work with a former PhD student, Daniela Lubick, at the Federal University of Rio de Janeiro, a postdoc student at University of Waterloo, Fei Wang, and Professor Henry Wolkowitz, also from the University of Waterloo. Okay, this is the problem that we address. This is the binary quadratic knapsack problem, where we maximize a non-concave quadratic function on binary variables. And we have only one constraint, the knapsack constraint. Well, on this problem, the binary variables are representing the decision of bringing or not n given items in a knapsack. And we have the profit of bringing each one of these items represented here in this matrix Q. On the diagonal of the matrix, we have the profit of bringing single elements. And out of the diagonal, we have here the profit of bringing pairs of items together in the knapsack. Well, each item has a weight, Wj, and the knapsack constraint here just imposes that the items that we carry in the knapsack doesn't exceed the capacity C of the knapsack. Okay, this problem is very well known from its application in investments problems. So in this case, C would represent the capital budget to invest, and there would be n possible investments. And the quadratic formulation models the case where the return of the investments considers the dependence between pairs of investments, not only on single investments, but the profit of investing in two investments together. Okay, besides the applications, the problem is very well known and investigated, also from being sub-problems on the solution approaches for more general binary quadratic problems. So for example, in column generation methods, sometimes it appears as a sub-problem. But here we are investigating not in the applications. We are interested not really in the applications, but more on the methodology for solving this problem exactly. And what we are going to propose here is a relaxation to obtain tight upper bounds for the problem. And these upper bounds, of course, are very important when we solve the problem exactly using, for example, branching bound type of algorithms. Okay, one standard approach to obtain these upper bounds is to construct a convex relaxation for the problem, lifting it to the matrix space defining by the symmetric matrix X, which will be given, will represent the product of the vector, the binary vector X times X transpose. So with this lifting, we can reformulate the problem with a linear objective function, given here by the trace of the matrix Q transpose X. In the non-convexity, then we bring to the set of constraints here. This is the only non-convexity of the formulation now. So the approaches that construct relaxations for the problem relax this identity in different forms. So doing this, we would have then, in this case, a formulation where we have a linear objective function and a convex set that would relax the feasible set of the problem. Here in this work, we are investigating only polytopes. So we have linear inequalities to represent our feasible set, which will define a polytope. Okay, another approach trying to improve these bounds would be to decompose this quadratic objective function, which is non-concave, into two parts, a sum of two other quadratic functions, where we guarantee that this first part here is concave if we impose that Q minus this perturbation matrix QP is negative semi-definite. So with this, we can construct a new relaxation for the problem, which is now a convex quadratic relaxation. We maximize a concave function where only the second part of our decomposition is linearized, is approximated. And doing this, what we are trying is to keep part of the quadratic information of the problem in the relaxation, so we can obtain better bounds by doing that. Our work now focuses on the selection of this perturbation matrix QP in order to obtain the best possible bound, and also on valid inequalities for the problem to tighten our relaxation of the feasible set. Okay, so let's start investigating how to optimize the selection of this matrix QP. We search for the decomposition of the objective function that minimize the upper bound that will be given by this relaxation. So what we do is to formulate a parametric problem on the parameter, the matrix parameter QP, which will minimize the upper bound given by the relaxation, subject only to the constraint that Q minus QP is negative semi-definite. And remember that this is what we need to assure that our relaxation is convex. So we are maximizing a concave quadratic function in this way. Okay, to optimize this parametric problem, we propose an interior point method. So at each iteration, we minimize this log barrier problem. We solve this log barrier problem here. And we decrease the barrier parameter mu at each iteration, converging to the optimal solution of the relaxation. Okay, we note here that the first term on this barrier function is the optimal solution of the relaxation for a given perturbation QP. And the second term is our barrier term. So this guarantees that at each iteration of the algorithm, we are inside the feasible set, in the interior of the feasible set, which means that Q minus QP is in fact negative definite at each iteration of the algorithm. Here we have the Lagrangian function, and of course to apply the interior point method, we have to derivate the Lagrangian function. So we have some observations here that are important concerning the first term here of the Lagrangian function. Okay, first we note that our relaxation can be rewritten like this. Function of QP is differentiable at every point such that Q minus QP is negative definite. And at these points, the gradient of the function P star is actually given by the matrix X minus the vector, the binary vector X times X transpose, where the matrix and the binary vectors are actually the optimal solution of the relaxation here. Okay, so in our interior point method, we then approximate the Hessian of P star using a BFGS method, and we use a quasi-Newton direction at each iteration of the interior point method. Now we note that to compute the direction, we need this derivative. So we need the optimal solution of the relaxation, X, the big X and small x. So the point is that our relaxation is solved at each iteration of our interior point method, each time for a new perturbation QP. And as we are optimizing this perturbation, we hope that at each iteration we obtain a better bound, a tighter bound. There is finally another important characteristic here of our framework, which is the fact that at each iteration that we solve the relaxation, we not only have a new perturbation matrix QP, but we also solve separation problem to add cuts to strengthen the relaxation. Okay, so the next part of the talk is devoted to identify which are the valid inequalities in the cuts that we use in our formulation, in our relaxation. On the initial relaxation, we just use this classic inequalities from the literature. For example, we take advantage of the fact that the variables are binary, so we impose that the diagonal of the matrix X is equal to the vector X, the binary vector X. Let me see how. Rosiane, please tell me when 5 minutes, okay? And okay, we also use the well-known McCormick inequalities, where we multiply the inequalities that give the bounds for the variables, the binary variables, and then of course we linearize the quadratic and bilinear terms, replacing them by the corresponding elements on the matrix. Finally, we also use inequalities that are derived from our knapsack constraint, just multiplying them by xi and 1 minus xi also. Okay, we propose some cuts, some valid inequalities that are also derived from the well-known Culver inequalities. A Culver is a subset of the set of elements to put in the knapsack, such that the sum of the weights of the elements in the Culver exceed the capacity of the knapsack. So the Culver inequality just assures that all the elements in the Culver are not in the solution. Okay. So now we have more valid inequalities on these matrix variables, where we just multiply the Culver inequality, a given Culver inequality, by again the variable xi and 1 minus xi, like we did before. We call these inequalities generalized Culver inequalities, and these are one of the cuts that we add to our relaxation. And now we propose some new valid cuts that are also derived from the Culver inequalities. Here we just note that very simple observation that if no more than beta items in a Culver can be in the solution, then if we consider all the two combinations of the items in the Culver, then the sum of the elements of X, of the matrix X corresponding to these combinations cannot be greater than beta choose 2. So this leads to these inequalities here, and it's very easy to see that if a Culver inequality like this is valid for our problem, then the Culver inequality in the lifted space derived from it, it's also valid for the relaxation in the lifted space. This is just an illustration of this cut. For example, we suppose we have a Culver with just 3 elements, 1, 2, and 3. These are all the 2 combinations of the items in the Culver. So of course, if not all the items can be in the solution, then only one of these combinations can be in the solution, and this is what our new cut is assuring. Here we have another set of cuts that we use in our relaxation, which uses a very similar idea. Again, it's derived from a Culver inequality, but now we get our Culver, our set C, and partition C into subsets of 2 elements. This is if the number of elements in C is even. If it's odd, we just take each of the elements of C and then partition the remaining set. While doing this, it's also straightforward to verify that these inequalities, all of them for each of the partitions, are also valid for our relaxation in the lifted space if the cover inequality here is valid for the problem. So an illustration of this new set of cuts again, we suppose we have a cover with 3 elements only, and this would be all the partitions of our set C. As I said, we take each one of the elements, and then we have only one subset with 2 elements. So if not all the elements can be in the solution, again, we can see that only one of the subsets in each of these partitions that correspond to elements can be in the solution. So we generate all these cuts here.
4-minute warning.
2 minutes, is that? Okay, so we propose this framework to get this upper bound for the problem. Here we have our relaxation. We start with this relaxation and then we apply our interior point method to optimize the perturbation matrix Q and apply cutting planes to generate the valid inequalities at the iterations of the interior point method. So we alternate between optimizing the perturbation and adding cuts to the relaxation. At every m iterations we use in our test m equal to 10, we solve separation problems to add these cuts to our relaxation. So here in our test, we are actually solving these separation problems exactly. We have integer programming formulations to separate the cuts. Okay, when the cuts are added to the relaxation, we want to emphasize that the search direction of the interior point method will change accordingly, because to compute this direction, we have to solve the relaxation, so we consider the cuts that have been added. So at every iteration of the method, we have an upper bound, which is computed by the solution of the convex relaxation corresponding to the current matrix QP. And finally, I present some results here, numerical results. We have solved instances with 50 and 100 items to put in the knapsack. And we see here that with our cutting plane algorithm, it's not embedded in a branching bound framework yet, it's just the cutting plane, okay? We could solve to optimality 5 out of these 10 instances, and the gaps are good for the other ones too. We have still big times here, and this is also due to the fact mainly that we are solving our separation problems exactly. So now we are working on trying to decrease these times, for example, using heuristics to separate our cuts. So this is, we have a paper on this, but we are still working on it to try to improve our computational results. And okay, thank you, that's all.
Okay, thank you again, Marcia. As I said before, the questions can be formulated by chat at any time, but the answers, all the answers will be given at the end, okay? So we will start the second lecture, which will be given by Andrés Medaglia from Colombia.
Marcia, could you please stop sharing your screen?
Yes,
thank you.
Please. Andrés, please.
Okay, thank you.
Share your screen. Okay, and so Andrés Medaglia is professor of industrial engineering at University de Los Andes in Bogotá, Colombia, and is director of the research center Centro para la Optimización y Probabilidad Aplicada. Andrés holds a PhD in operations research from North Carolina State University, and his current research interests include the development and applications of optimization techniques to transportation and logistics, health systems, agricultural systems, and engineering design. He has served as secretary and vice president of the Latin Hybrid American Association of Operations Research, ALIO, and as Vice President of the Colombian Operational Research Society, ASOCIO. In IFORS, he served as the liaison for the Americas, and he has been the recipient of several prizes, such as the IFORS and also the IFORS prize of the last edition in Quebec City, Canada, in 2017. His lecture is entitled Level of Traffic Stress in Bogotá, Towards a Friendly City for Cyclists. Thanks again, Andres. You can start, please.
Thank you, Roseanne.
20 minutes.
Good. Okay. So you can see the screen? Yeah.
Yes.
Okay. So first of all, I would like to thank Grazia, Willy, and Roseanne for inviting me to the IFORS Global webinar series and for the kind of introduction of Roseanne. So today I'm going to talk about this level of traffic stress. And this is a joint work with colleagues and students from the School of Medicine, Civil and Industrial Engineering, and also Fundación Despacio. So this work is part of a larger project called Salurbal, which main goal is to make cities healthier, more equitable, and environmentally sustainable. So, and what I like most about this project is that it captures innovation from our region and embraces it, and it takes them as lessons for the world. So I think that's very nice objective. So Salurbal has many local actors spread throughout the Americas, and it is funded by the Wellcome Trust from the UK and is led by Ana Diaz-Ru, an Argentinian public health expert from Drexel. So why is the interest in Latin America? Actually, well, our region is under rapid urbanization. 80% of the total population they live in cities, and our cities have a very diverse urban landscape, and we have great contrasts, like big mega cities like Sao Paulo or Bogota, and small and more cohesive cities also. So there is a diverse landscape. And also we face great challenges in terms of social inequality gaps, and that makes our region, these three reasons make our region a perfect lab to learn some of the lessons that we have addressed in different aspects. So the project posed several aims, and we have been working with my colleagues putting together OR models at the service of this project. And when I talk about OR models, you will see it's in a very wide sense, because we're using descriptive models, predictive models, and prescriptive models as well. And we put them at service of these aims 2 and 3. In particular, I'm going to talk about a methodology that we devised that is connected with these 4 pillars: mobility, social inclusion, comprehensive urban development, and also promotion of healthy behaviors. So specifically, our objectives for this work are, first, we would like to design a methodology that is able to classify the whole road networks of the city according to the level of stress that it imposes to cyclists. Second, we would like to not only include physical information that it's usually often found in LTS metrics, but we also want to add some functional characteristics of the road network. And third, we would like to estimate the LTS for larger cities, like mega cities like Bogota. So we need to scale this methodology in an economic and scalable way. So in this article, you can find the details of this methodology, and I'm going to present briefly what it's about, but the full details, you can find them in this open access article. So let me start from the beginning. So what is the level of traffic stress? What do we understand by stress in this framework? So the level of traffic stress is an indicator that classifies the road segments according to the stress experienced by a cyclist. So we can see that from the image. In the left, you see that if cars pass by your side while you're riding the bike and they pass fast, you might feel uncomfortable, threatened, and possibly in danger. On the other hand, if you see the picture on the right, and if you're riding your bike on a segregated pathway, you might feel more secure. So with this idea, in the LTS literature, depending on the characteristics of the road segment, the street is classified in one of those 4 levels. So typically LTS1 are streets that are the least stressful roads. Imagine something that is suitable even for kids. On the other end of the spectrum, you find LTS4 streets that are in general more stressful and are suitable only for the most strong and fearless cyclists, those that can wade through vehicles in heavy traffic, for instance. So let me try to navigate you through this methodology that we use to estimate this level of traffic stress. And let's start with the data, with the variable selection. After a lot of discussion among the transportation experts, urban planners, and public health experts in our group, and with transportation officials in the city, we decided to use these variables to classify the roads by the stress level. And we divided these variables into groups, basically the physical variables, which are often used in the literature, as I said, but we also added some functional variables that transportation experts thought were really important. So the first variable is the width of the road segment. So basically, we measured that width from border to border. And you can imagine that if you are considering a road segment like a boulevard, that it's wider than residential street, you might feel more stress on those boulevards, okay? Another variable is the number of lanes in a road segment, and as well, if you have a large number of lanes, you might have a more stressful road. Another variable is this binary variable that signals if a given road segment has a segregated cycling lane running along that road segment. Another variable could be, and it's very, very important, and we have always all probably experienced this, if there are heavy vehicles passing by through that road segment, you might feel also stressed. So this is a binary variable that indicates if there is a presence of heavy vehicles, for instance, buses, okay? And with respect to the functional variables, traffic can be expressed in different terms, like vehicle speed, measured in kilometers per hour, traffic density measured in vehicles per kilometer, traffic flow measured in vehicles per hour, and also in congestion as an index. And to calculate these variables, we had to use the Google API to calculate a proxy of the free flow traversing time and also historical traversing times. So in summary, these are the 8 variables that we use to calculate these LTS. Once we had calculated these variables, so we went through a second phase, which is the unsupervised learning phase. That it's the one that it's in charge of finding these categories. So we use cluster analysis to identify the road segments that were very similar in terms of those 8 characteristics, 8 variables that we defined. And we also try to make them different, those clusters, to the other clusters that group segments that are alike. And based on this silhouette width analysis, we found that 4 clusters were reasonable to classify our road network. And that was a happy coincidence, a very nice coincidence because it matched what it's often used in the literature, this 4-level classification. Okay, of course, in our case, they are not exactly the same in terms of the interpretation, but the nice thing is that we also have a few number of clusters that are able to classify the whole road network. So in particular, in the city of Bogota, we have about 170,000 road segments. So the clustering algorithm has some challenges, especially in the distance that we are using to measure the distance between these road segments. So we needed to scale this classification algorithm. So for that purpose, we use also, or we coupled that with a supervised learning algorithm. So we choose, and this is how it works. Basically, we have the map of the city here. We choose one locality, imagine like one district. And in this case is a district called Usaquén. And we classified with the clustering algorithm the road segments in this district. So we have these 4 clusters, all the road segments in this locality classified in these 4 clusters. Then what we did was we trained multinomial logistic regression. So with that, the result of this regression, we now are able to predict the probability of belonging to one of those 4 clusters. And with that score, we were able to expand that to the whole city, okay? That's the procedure that we use to scale the procedure. Finally, we sat with the experts to label and to understand each of those 4 clusters that we found. So in this graph, in this radar graph that we are showing here, you can see the 8 variables. And we also have 4 lines representing each of the 4 clusters. So if I take like the inner line, which is the light green line, we have that those are that cluster, that category represents roads that have low congestion, low traffic flow, low speed, few number of lanes, narrow streets. Also, there is also no presence of heavy vehicles, and also there is lack of cycling infrastructure. This is a bit counterintuitive, but it's how it worked in our case. And in this case, we have like this cluster of that represents like low stress level, a low stress level, and that's one cluster. And we did something similar with the other clusters, understanding a little bit of these different variables, how they were representing the cluster. And we in summary, what we did was we found these 4 labels and we labeled them as low, medium, high, and extremely high. So finally, after these 2-step classifier that we built, we came up with a dashboard that where we were able to visualize the results, and also, of course, engage with transportation officials. So here we can see the LTS layer that I just described, like the output of the information for a given neighborhood. So we can see in this left side figure, is the figure in the left, is that like these wider roads are busy and wide, and they tend to be LTS4. That's why they're pictured as extremely high or red roads, or even orange, meaning that they are highly stressful roads. On the other hand, you can also see that the residential streets are labeled like a low stress level, with a low stress level. So these are the results in a pictorial way. In the literature, it has been proved also that more accidents occur in segments labeled with a higher level of stress, say LTS 3 and 4. So what we try to do here is that we overlap our result with this LTS layer and geographical layer with our results of the classification algorithm, and we match that with the reported fatal and non-fatal collisions in the city. And as expected, what we found is that the fatal and non-fatal accidents increase as the LTS level increases. So that was a good validation that we were doing something that was according with the perception of stress and the collisions that were happening in the city. So in conclusion, our methodology provides these context sensitive and adaptable LTS based classification. When we say context sensitive, I mean that we can scale these to different cities and taking into account the specific variables that we can find in different cities. And in our case, the case of Bogota, we found 4 different levels, meaning low, medium, high, and extremely high stress categories. And our clustering method also was able to embed not only physical attributes of the road segments, but also functional attributes. That was an interesting thing. And something that is quite interesting for us is that this methodology allowed planners to predict the impact of planned interventions, because at the end we have like this score that can be used if we have a new intervention in parts of the city where we're going to plan some kind of roads. We can use that score to find that this road might be stressful, less or more stressful. So that's an interesting thing to have. Also, there are ties with optimization. Of course, what I have described so far are predictive models, but the nice thing is that we are currently using these outputs of the predictive models to couple them with optimization models. And as a response of this COVID-19 crisis, in more than 90 cities in 20 countries around the world, the transportation officials have been implementing these temporary cycling paths as an alternative for transportation, for safe transportation. So with this output of the predictive models, we now have valuable input to build optimization problems that help us to design a better cycling, low stressful infrastructure. And actually this problem is a network design problem. So that's one line of research that we are pursuing right now. Also, as part of this Cerebral project, we are developing other models that measure the likelihood of using the bike in the city. So because in our data set, we have only origins and destinations, we don't know actually the route that a given cyclist use. So what we are doing now is we are estimating using shortest paths, these estimate of the actual route. But because we don't have certainty that this is the right path, what we are using is we are computing this buffer that I'm showing here within that encapsulates this shortest path. And we are considering the factors that affect biking within that buffer, okay? So my point here is that we are using generalized additive models, which are statistical models, but part of the variables that we're using are powered by optimization. This is another way where we are linking optimization into these statistical models. Finally, to assess the yep. Mary?
2 minutes, please.
Yeah, perfect.
Yes, 2 minutes, please.
Perfect. So, and finally, what we're using now is also to assess transport inequalities. We are calculating this index called the TOI, the Transit Opportunity Index. And this is a nice index that captures accessibility and connectivity of the public transport system. okay? And because in the project we are trying to assess the impact of innovations that are happening in the transportation area in the city, like electrical cable cars, we need to measure the impact of these interventions before and after, okay? So to do that, what the connectivity component of this index, it requires the solution of massive shortest paths in large-scale time-space networks, and this is happening behind the scene. And with that, we can calculate this kind of metric in a very visual way. And basically, this is the way we visualize that. Basically, it's taking the origins, and we are clustering the origins in localities. And if we have a white bar, this means that this locality has a very good access to the cities. From that locality, it's very easy to reach the city. And similarly, we can see the destination. And with this, we are grouping them or sorting them in terms of the income. And we can see that, for example, this blue locality has it's very difficult to access the transportation system and reach the city. If we compare that with the gray locality, which has access to a wider part of the city. So with that, we can assess the lack of equity in transportation. And with that, I conclude. Thank you.
Thank you, Andres. Please. Once again, the questions will be answered at the end of all lectures, okay? You can write your question at any time in the questions and answers box, and please indicate your country and the speaker, if the case. So let's start the third lecture, which will be given by Roger Rios from Mexico. Okay. Roger Rios is currently a professor of operations research in the graduate program in systems engineering at Department of Mechanical and Electrical Engineering, Universidad Autónoma de Nuevo León, in San Nicolás de los Garza, Mexico. He earned his PhD in operations research from the University of Texas at Austin, and he has held postdoctoral and visiting positions at the same university, Texas at Austin. And Roger has received several awards throughout her career, having a strong presence in the international scientific community of operations research. And he is member of the Mexican Operational Society. And last year, he was chair of IFORS ALIO in Cancun, Mexico. So, Roger, thank you again. The lecture of the Roger is entitled "A Case Study on the Potential Impact of a Kidney Extent." Roger, thank you again. You have 20 minutes, please.
Okay, thank you. Okay. Yeah, well, before I get started, I just would like, again, thank all the organizers for this wonderful idea of having this webinar series for all people around the world. And I joined the request made by Marcia about, having this type of activities being available to the worldwide people, because I understand, the pandemic is going to be over someday, but again, particularly in our developing countries, many people, many students, they can afford to go to some important conferences. So if we have these kind of activities, considering the future, it will be a great asset to our many people around the world. So I congratulate you for this effort, and well, let's get down to the amazing kidney exchange world, which is going to be the subject of today's talk. And let me just, okay. This is an effort that we have made over the past, let's say, 3-4 years, working with a few people on trying to understand and implement this kind of programs in Mexico. Here's some of the people that have actually worked with us. It's our colleague from the medicine school, Homero, and then Summer Gentry, which is in the United States Naval Academy in the US. And our former grad students, Caro, Mitchell, and Jessica. Caro is now pursuing her PhD in the University of Toronto, working on the same subject. And well, this somehow contains some of the ideas found over the past 3 years. Now, of course, this is the outline of my presentation. The heart of the talk is point number 3. You know, the main contribution of this talk is you know, present a case study with real world data from Mexican and hospitals and Mexican population. And of course, before getting to that point, we still need to talk a little bit about what motivates the problem and a few basic models. Even though we're really using existing models and solution algorithms, it would be a good idea to take a look at those so you could have a feeling what they look like. And okay, so what is a kidney exchange? Okay, well, it's well known that people, in many cases, they need organs to any type of organs to sometimes to survive or to have a better life. And most of the cases, you have to wait for someone to die to get an organ. Now, kidneys are a very unique and particular type of organ. Why? Because, well, people have 2 kidneys. And well, when one of your kidneys fail, you still have the other one who does the job, and then you'll be okay. However, when your second kidney fail, that's when trouble starts. Why? Because now you have to undergo treatment to the dialysis treatment to try to do the job of the kidney who is in failure, or you have to wait for to have a donation from either a deceased or a living donor. In the other hand, in the opposite side, well, you could also, you know, if both of your kidneys are working fine, you could donate 1 kidney, and if you are left with a kidney, you can live without any problem. Now, what are some important facts about this? Now, you know, for those having, kidney disease, what it's called end-stage kidney disease, you know, the dialysis treatment is very, very annoying and very, very expensive. Just in Mexico, it is an estimated that about 200,000 pesos costs the government to give treatment to a person. And if we have a waiting line for people to get a kidney of about 17,000 people as of last year. And so you make the multiplication, that's an astronomical figure for Mexican standards. And of course, these figures are also consistent with the statistics in other countries. Now, of course, given this, it's clear that transplantation is preferred over treatment. Now, in particularly, we distinguish 2 types of transplantation, or 2 types of donations. One comes from deceased donors and one from living donors. Now, the issue with deceased donor is that it has to be performed within 24 hours of the people who died. This means that you have to do a lot of logistical effort between the moment in which people die to the moment in which the kidney is actually carried and transported to the first person on line of the waiting list. Of course, given this particular feature, it is impossible to plan anything. Just basically you wait for people to die and then to try to get the kidney as soon as possible to the first people in line who is compatible. Now, in the other hand, this other problem, it's very related to having long waiting lists because, well, at least in Mexico, we don't have the culture of donation. Even when you are dead, That is, if you die, even though you put it in your travel, into driver's license, you check a mark that you are willing to give your organs. What happens in reality is that they still have to ask your mother or your living parent, whoever is there, and then if they say no, even though you mark yes, they won't give it to you. So it's a cultural issue there. But what it means is that we have a very large waiting list, and then we have more people in need of kidney transplant that there are available organs. Now this opens up the possibility of living donor donation, which means, or in other words, it's also called an exchange. Now before setting the details of what an exchange is, it's very important to talk about compatibility, because this is the key part about kidney exchange. In the table below, right here, we have a compatibility chart of the blood type. Well, we have this is the recipient and this is the donor. As you can see, not any people can donate to any people, right? So for instance, a type O, it's called a universal donor because it can donate to any blood type. However, a type AB, it can donate only to type AB type of person. Now, what am I mentioning this? Because the living donor procedure implies that, well, if you are in need of a kidney, and then you get a person, usually it is a person that loves you very much, your mom, your dad, your brother, a close relative, a close friend, willing to give a donor. Now, if the donor is compatible with the patient or the recipient, then the problem is solved. Well, because they just perform the operation. The problem is that in most of the cases this doesn't happen. They are incompatible. So this is where the exchange idea comes into play. Now, what is an exchange? Well, I'm gonna explain two different types of exchanges. We have cyclic exchanges and chain exchanges. Now, what is a cyclic exchange? Well, suppose that you have one pair of incompatible donors, which is this family one over here, and then you have another one over here. If they may be incompatible, but if they can exchange kidneys, then you would get like a 2-pair kidney exchange. So, and then you could save both lives, right? In the other hand, well, not only there are 2 cycle exchanges. Of course, we may have 3 cycle exchanges illustrated in this case over here, where you have 3 different pairs, and then this would give to this one, this would give to this one, and this would give to this one, right? And of course, you can think that you may have 4, 5 pair exchanges. However, in practice, that doesn't happen because, when you perform a cyclic exchange, I mean, the surgeries have to be taken at the same time, that is simultaneously. So it is like a medical fair play, right? Because even though nowadays surgeries are very precise and very highly successful, there's still some, a low probability measure that have to be addressed fairly. So this has to be taken at the same place. So if you want to perform a 3-cyclic exchange, you need 6 surgery rooms available at the same time. And for many hospitals, that is a very logistical burden that they cannot take. So in most of the cases, you will see that 2 or 3 cycle exchanges, and very, very rarely you will see something above 3. Now that is for cycles. Now the other type of exchange is what we call chains, and this is a chain. Now the chain is started or triggered when you have an altruistic donor, someone willing to give the kidney just for the altruistically, and then what happened is that you have all these pairs of incompatible pairs in between, and this would give to this one, this to this one, and then the very last one would give to the waiting list, right? So in this case, in contrast with the cyclist, this doesn't have to be performed at the same time, though they could be performed over a period of time, and that leaves the option of having very long chains available for surgery. Now, So in just as a summary, so what is the optimization problem involved? Well, given a compatibility graph formed by nodes, which are the set of incompatible pairs, which is P, the set of altruistic donors, and the set of edges is all these arcs that join a compatible surgery that can be performed, right? Taking into account the blood type. Now, here we have a weight, which for the time being, assume that this weight is equal to 1. At the end of the talk, if I have time, I will talk more about these weights. But here, under the assumption that this weight is equal to 1, the object is to find the maximum cardinality of the total number of cycles and chains, because that would match the maximum number of people that I could that we could save because of these exchanges, right? Now, this is what a graph, a compatibility graph, looks like. Here you have all your patients, which are your incompatible pairs. Here you have your altruistic donors. Of course, when you don't have altruistic donors, then you would solve models with cycles only. And when you have altruistic donors, you can solve models with cycles and chains. And of course, that leads to different models, right? And then now in the next 3 or 4 slides, I have a few examples that I'm going to skip, so I could try to finish my talk in time. And but those of you who want to a copy of the talk, just email me, and then I will be happy to share this. Now, here, these type of kidney exchange programs, they have been developed in other countries. For instance, the very first country that I know of that developed this idea was South Korea in the early 90s. And then in Europe, in the Netherlands was the first country that implemented this kind of program, 2004. And then, of course, in North America, the past 15 to 20 years have been very, very active in this area over here. Actually, there are some countries where they have different organizations that organize this kidney exchange. For instance, in the US, they have different organizations. And in some other countries, there's a unique nationwide organization, right? Now, the issue here is that in Mexico, we don't have anything. I mean, we don't have yeah, of course, we have the capability of performing exchanges, but we don't have like a systematic program that, given a database or a pool of incompatible pairs, that would find all possible exchanges. So we don't have that thing. So the main goal of the motivation of this research was to collect some real world information from the Mexican population, from Mexican databases, and trying to show the Mexican health authorities that this is a valuable and very impactful thing to do for people. Now, in this particular talk, I'm gonna be just showing our results. Applying the existing models with the existing solution algorithms to particular databases. Of course, we also have done some research on developing new models and algorithms, but that is the subject of a different talk, not here. So here I'm gonna just briefly mention that this is just a few of the works, a few of the models that have been developed in the past. There are, of course, models based on cycles, models based on cycle and change. This list is by no means exhaustive. This is just a sample. There's, of course, a lot of work that have been done in this area. Now, I'm going to skip through some of the models that I put here just to have the talk self-contained, and I'm going to jump to the computational study for my last 3 minutes. Of course, this is taken from different databases. We have 2 local hospitals, the University Hospital with 15 patients, San Jose Hospital, 35 patients. And then we have the statewide hospital in the state of Nuevo León. We are not here, just close to Texas. This is Texas over here. This is my state of Nuevo León with around 1,000 patients. And then we were able to get a hold of the nationwide registry with about 17,000 patients. Now, even though we have the complete information of the patients, because like I told you, this donor program doesn't exist in Mexico, we don't have information about the donors. So we simulate the donors using information from the Mexican blood type distribution, real world Mexican blood type distribution. And then we generated 20 instances for each particular case, and we are showing averages, right? Of course, we want to measure what is the impact of cycle only and chain only models and the impact of cycle and chain models. Now, This chart over here, what it's showing is the results when I tried the database of the University Hospital, it's only 15 patients. It's a very, very small sample. But here, this chart over here on the left is the results, when I apply the 2-cycle model. That is a model that allows to find cycles of up to size 2. And this one, when I apply the model that will allow us to solve a problem with allowing cycles of length 2 or 3. And well, as we could see, well, on average, this turned out to be better, and that's a very logical result because this feasible region is larger than this one. So in average, it jumps from 2 to 3. And then when I go to the other database, the one with 35 patients, same results from the San Jose Hospital. So we have an average of around 6 to an average of around 11, almost double out of those 35 patients by allowing, models of size 3. Now, here, this is a very interesting slide because now I'm using the database from 1,000 patients from the state of Nuevo León. And here, because we don't have donors, well, what we're showing over here in the horizontal axis, it's what would happen if 10% of these 1,000 people would bring donors. If 20% would be donors. For instance, this, say this column over here, it would be the result of having around 108 donors out of these 1,000 patients. So as we could see the result, it's you could say that around 30 to 40% of the people would be safe. And we could see always that the 3-cycle models dominate 2-cycle models, and that's a logical thing to do. Now, this is the very optimistic case where, if all these people would bring each their donors, then we would save around 500 people, almost half of them. Now this is the same result, but now showing the national database, 17,000 people. So this column over here means that now that if 10% of these 17,000 people would bring donors for the exchange, then after optimizing, we would be saving on average about 300 people, and so on and so forth. We could see this tremendous growth, which illustrate the fact that the more people we convince to participate in this thing, the more people we benefit, and this is very important. Now I'm going to jump to my last. I'm going to jump these two, and I'm going to show this to wrap up my presentation. These last slides, which is this is actually a pretty neat slide that actually is the one that we tried to sell this idea to our local hospitals. Now here again, we are solving the model with allowing cycles and chains, and here we are using the databases of the local hospital, the University Hospital and San Jose Hospital. These columns over here, those are the individual results, and this third column over here is the sum of these two. That is, we solve individually and then we sum. Now this over here shows the results when we combine both databases before optimizing. So as we could see, the result of combining the databases, it's significantly better than just solving the database individually. So in the bottom line, the sharing information pays off rather than solving individually this problem. Now, this last slide is going to show what the future is for us. Here we are in the year 2018. Up to this point, all this is real data. The green line over here is the projected growth of our waiting list. This is the number of patients in the waiting list here in Mexico. So, and there's this red line over here, the red dot, it's what would happen if we implemented in Mexico a nationwide program, assuming a 10% donation. So we will see the impact if we don't do anything about soon, I mean, things don't look pretty good, right? So, and with this, I think I'm over my 20 minutes now. I'm gonna just wrap up my presentation. Of course, this is something that's very important. There's also some very research-oriented issues that like solving large-scale instances, solving a stochastic heat exchange problem, doing multi-country type of programs, which some countries have already participated in these kind of activities. And then Finally, just to thank some of the people who have either sharing some of their computer code or giving us some pointers about problems. And I think that's it for me. Thank you very much.